Morning, afternoon, sorry about that. And the final exam is scheduled on the Friday morning, 7:30 and 9:30 a.m. In the week of May 10th. So that may be a little bit too early for a lot of us, including myself. So to better prepare ourselves, we probably will do a online exam like we've been doing for midterms. And the time will probably gonna be on Friday afternoon, 1 to 4 o'clock. And if that time doesn't work for us, we can consider changing it to Thursday, 1 to 4 o'clock in the PM. And if you have conflicts, please send me email quickly as soon as you can.
I just joined. What is this exam about?
Yeah, this is the final exam that is by the calendar has been scheduled on a Friday morning, 7:30 to 9:30 a.m. I believe, and that's on the week of May 10th. So I think that's a little bit early for us. So I'd like to suggest to change the time to afternoon, 1 to 4 p.m. On that day, Friday. And if the time doesn't work for us, we can also consider 1 to 4 p.m. on Thursday before that. So just send me email if you have any other conflict in terms of finals. Okay, is that clear? All right. So one more thing about the final exam. The content of the final exam will be similar. Sorry, that shouldn't be say content. The format or the style of the final exam is going to be similar to the midterms. So we'll release online, and you take it and open book, open notes. Pretty much everything's open. Just no communication among the students, and you have 3 hours to finish that. And the content of the final, it's I would like to say sectional, mainly focus on the column design and service deflection that we cover and the development lens we cover so far. But one bit of caveat is that the final is going to be a little bit longer. So we have probably 4 problems, and problem 1 or 2 will be multiple choices. In problem 1 or 2, you might see some familiar problems from previous exam, like exam 1 and then 2, in terms of flexure and shear. Okay, I haven't made exam yet, but I would not use any of the old exam on final exam. Now, if you have seen some similarities of the past midterms from previous midterms, like previous semesters, that won't happen in the final. Okay, let me say this clearly. For the final exam, there will be brand new problem that you never seen before. So that's going to be on the final. And we will have a review session for the final, so I wouldn't worry about it. And I also go through some typical problem that we're going to cover for the final exams. Okay. So any question for me about the final exam and the arrangement, the schedule, and all that? Anything? Not yet. Well, I guess it's still early. Okay. So if you find your schedule that you have some conflicts, say you have finals on Thursdays or Friday in the afternoon, just email me so I can coordinate and change the time accordingly. Okay. All right. Now, about quiz 9 and homework number 7 on the core section, right? Moment, inertia, cracking, and all that. I received some questions. I just want to quickly address them before we start the official lecture today. Okay. So give me 1 second. Let me open up my laptop. Sorry, iPad on this thing. Okay. So mainly focus on how to calculate the cracking moment of the section. All right. So here, I believe it is. This is bounding 21. This is what? Okay. So share screen, iPad. Oops. All right. All right. Okay. All right. So the main issue is about the cracking moment actually. So let me go back here, and this is the quiz number 9, I believe. Okay. So I received some comments of people asking whether, you know, the number is what I got, which means that if you get a different number, is that the case? All right. So there are quick things. First of all, we have talked about IGT. Okay. IGT. So that is so-called transformed gross moment of inertia. All right. Transformed. Now, what does this word mean anyway? Transform. That means account for steel. Okay, account for steel reinforcement. Okay, so whenever you see this little subscript T here, it means that if I'm gonna make an example of this I regular section, if I have reinforcement, whether it is at the top or at the bottom, when I transform, that means I will have to remove that first and add little wings here. Okay, and you know this little wings here is n minus 1 as. Okay, and this top is n minus 1 as prime. Now this, after you get this and you get IGT, and this is IGT, means transformed, okay? Transformed. But on the other hand, now if you have a section, okay, and although I have reinforcement in it, and you might see this from other code and literatures online, okay? Now, if some people say IG, and actually in the homework, this also appears, IG, that means treat it as a rectangular section by omitting reinforcement, okay, omitting steel, all right? So that is the difference between this IGT and IG, okay? Now, I believe in homeworks, if you see the symbol, then you can ignore the reinforcement, okay? Just treat it as a rectangular section or whatever the geometry is for the concrete part. But if you see this IGT, that means you have to transform to equivalent concrete section first, okay? And remind you that this N here, right, was defined as modular ratio, means ES over EC. And for better, lack of better knowledge, if you don't know what it is, just assume it's 8, okay? Now, if in the exam you're in a rush, you don't know how to calculate or you forgot, and the Jiffy, you just have to guess a number. You guess 8, and I'll give you credits for it. Okay, so that is the carry away. Okay, so this is question number 1, basically. People asking what is the difference between IGT and IG. Now the second, question number 2, about the cracking moment. About the cracking moment. First of all, I still have friends asking me, look, Bob, if a rectangular section, well, that's not difficult, right? Let's just assume a T-beam like this, right? Where are T-beam? So I say, if I want to find out I crack positive, how do I do that, right? So when you're trying to find I crack positive, and you have steel reinforcement, right? So first of all, you have to convert that into a reinforcement in the steel here, okay, into concrete. And knowing that the bottom part is cracked, right? Bottom part is cracked. So neutral axis somewhere here, okay, or somewhere here, right? It doesn't really matter, right? Neutral axis is gonna be either here or here, right? So if your neutral axis is way below the flange, right, somewhere here, and you can just say, look, the concrete has lost its old tensile strength, and I just have steel, so I will convert this into an N, which is the modular ratio multiplied by AS, and that is the converted concrete from steel. All right. Now for the top part, you already have the shaded area, right? And supposed to be in compression, you may run into trouble. Remember how we talk about this? There's a KD, right? There's a KD. If you remember, there's some square root of something plus something, right? There's an equation for it. Okay. Now when KD is smaller than HF, that means the neutral axis stays in the flange, right? If the neutral axis stays in the flange, then you don't have any issue. But, okay, let me say this, but when KD, okay, KD is no longer within the flange, say bigger than HF, then you might not use KD for the calculation for T-beam, okay? T-beam or I-beam, you cannot use KD anymore. So the question is, what can I use for that? What can I use for that? Simple, right? So what you need to do is you can erase this part, assuming that this is no longer confined to HF, okay? You have this part instead, right? So what I would do is that I would say this is number 1, this is number 2, and the steel converted piece is number 3. I need to find a neutral axis, is that right? So how do I find neutral axis? by definition, right? By definition, the distance between the top fiber to the neutral axis is called y top, y bar top, right? Always, right? We like to use that, okay? So that number, that value should equal to what? The area of piece one, multiplied by the distance of the centroid of piece one to the top reference line here. So this is y1, right? y1. In this case, since the flange has a height of hf, I can quickly write out here, that y1 should equal to hf divided by 2. All right. And then you add up the 2, which is this piece right here, okay, area of that piece, multiplied by y2. And y2 is the distance from the center of 2 to the top reference line here, okay? So in that case, this is some area question mark, right? You don't know because you don't know this length here. You don't know this length here, right? So A2 in essence is equal to BW, which is the web thickness, okay? Web thickness multiplied by this x here. And what is x here is y top minus what? Minus HF, okay? Minus HF. HF is the flange height, right? So that is area for A2. And the distance between the center of 2 to the top, Y2 equal to HF plus y top, right? Minus HF, right? So it's just HF. Sorry, shouldn't be that. It's just HF plus half of y top minus HF. Okay, so that is y2. So this is y1, this is y2. Okay, sorry for my crazy drawing. Okay, so now that is that. Then divided by the total area, right? Total area. So this also have to get A3, Y3, and divided by A1 plus A2 plus A3. Now, what about A3, right? What about A3? So you look at this, A3 is what is converted still. So that is NAS, NAS. How about distance Y3? Y3 is nothing but depth of the section D here, which is normally given, right? So all these give you this equation here. So I'm just gonna plug them in and bear with me just for a second. I know this sounds crazy and a little bit long, but let's just play along with it, right? So A1, I forgot to mention here, is the area of the piece one, and that is essentially BF, which is the flange width, okay? Flange width BF, okay? Multiplied by HF, which is the height of the flange, right? And Y1 is half of HF, and that is easy, right? So now you have a very long equation here. So BF HF multiply HF divided by 2 plus A2 Y2. So A2, this fellow here, BW, Y top minus HF, and distance Y2 is this fellow here, HF plus half of Y top minus HF. Okay, now that is A2 plus Y2 plus A3 Y3. A3 is NAS. Y3 is what? Is this fellow here, which is simply just D as a depth, and divide by the total area, which is A1 right here, BF, HF, A2 right here, plus BW, Y top bar, minus HF, plus A3, NAS. Okay, and this is long because symbolic, right? This is symbolic equations. Okay, so this is the equation where you get a neutral axis. Now, if you have sharp eyes, and all of you should have, you notice that in this equation on the left, you have y top, y bar top, okay? But on the right, you also have y top, but in second order. So if you really get this equation, move this towards the right or move this bunk stuff towards left. Either way, you end up with an equation, the y top, and believe me or not, it is actually a second order equation, right? And that has to equal to 0. You have to actually solve for y top. Solve for y top, okay? All right, so that's how you get a neutral axis. for a T-beam like this, okay? Once you get a neutral axis, the rest should be easy, right? You can get ICR and you can get the stress due to the cracking moment, so on and so forth. Okay, so this part was not clearly stated in the previous content, so I just want to add up here. All right, now I will upload this as a separate note to the existing cracking section, but um, I want you to give a try on this philosophy here using this to find the Y top for T-beam and I-beam. Okay, but I promise you in the exam, you will not see this most likely. All right. In the exam, you will not see this most likely. Okay. All right. Any question on this so far? Anything? Folks, anything? Okay. Now this is a little bit long or a little bit time consuming to digest, but don't worry. I can extend the deadline for homework number 9 quizzes a few more days, but do try to follow the concept, understand this concept. If you don't, still don't, during the weekend, when you get bored playing video games, if you have time for it, I doubt it, or if you just really struggle and don't know what to do, desperate, just give me an email, okay? We can arrange individual session to help you out. Okay, we can arrange individual session to help you out because this content it's a borderline mechanics materials content. Okay, so I know some of you may have not really covered this in the mechanics materials lectures. Okay, that's why I'm adding this additional component here. All right, but for majority of us, don't panic because this is a little bit complicated and I don't think we'll have this section in the final. Okay, in the final. All right, all right. Any questions on this? Final call. Any question on this? All right. Okay. Well, if not, like I said, I'll upload this notes to the Canvas, and I know the drawing is a little bit crazy. Try to follow and go back to watch the video. If it's not clear enough, email me, okay? I'll give you a few tutorial over the weekend. Nothing else I'm doing anyway, okay? All righty. Okay. So with that, let's get back to the main lecture, okay? Main track. So bonding, right? Bonding. And we have shown what the bonding looks like, right? So a quick recall, what is bonding, right? Bonding is in the form of us in a practical sense is the development lens. Development lens, okay? So take a deep breath. Let's get back to the track on the definition of development lens. The definition of development lens is that if I have a bar embedded inside the concrete and being pulled away, yanked away from the concrete, I need some lens to develop the stress in the bar, right? So in a short term, that is the lens it takes from zero stress in the steel to the yield strength of the steel, and that lens is called a development lens. All right, that is called a development lens. And development lens have different category, right? Tension, compression, and for hooked bar. The case I show here, this is actually a hooked bar, okay? This is actually a hooked bar. But in reality, or in this lecture here, we most often see is tension straight bars, okay? So we're gonna put our emphasis on the tension of straight bars, tension of straight bars. Okay, now talk about the development lens. Naturally, we have to talk about bonding. Okay, so we've shown last time there's a bonding mechanism plot here. And you may find this is boring. You say, look, Bob, I just want an equation, right? Why don't you show me the equation instead of going through all these hooplas, right? So let me stop sharing and reshare. Something wrong with my slides here, okay? Give me 1 second, sorry about that. My internet is always hectic on Thursday. Okay, 1 second. All right, we're back. Okay, so when we talk about the bonding, right, why it is so important, why I have to show you and you have to remember is because we will have this in the exam. All right, typical short answer question I can ask, following for which is not the bonding component, sorry, which is not one component of bonding resistance. A, friction, B, chemical adhesion, 3, bearing, D, concrete compression, naturally the last one, right? Concrete compression, right? So the aim of this part is to ask you to understand that there are 3 critical components for the bonding stress. That is the friction, chemical adhesion, and bearing on the by the deformation of concrete. So people may ask me, hey Bob, what does bearing mean? Right? Bearing means that when I pull the bars, these ribs on the bar will work against the concrete that's surrounding it to cause a compression at the local joint, at the local junction here. So this mechanical bearing give you bearing forces and stresses, and that is the bearing action in the bonding. Okay, so friction, adhesion, and bearing, these three components consists the bonding stresses along the bar. And if you think of it, the development length is simply that stress in the bar developed from 0 to the yield strength. So if I really want to make a total add up, I add all these force, add all these stresses up, and they finally will reach the yield strength of the bar. Finally, we reach the yield strength of the bar. Okay, so that, ladies and gentlemen, is the bonding reaction, bonding mechanism. Okay, so with that, we say, look, now we have understood the bonding mechanism, right? We need to calculate, and this is the practical part, the development length, that is the equation of the scenario, right? What is in this equation? First of all, lambda in the equation, and lambda is a indication of lightweight or normal weight concrete. And I never talked about this in detail, but why lambda always equal to 1 in most cases and 0.75 in low weight? That is all something to do with the strength of the concrete. So the lower density is, the weaker the concrete is, right? So if I have a stronger concrete, then I have more strength provided by square root f prime c. So I will end up a shorter length, developed length to reach the stress in the steel. But if I have a lightweight concrete, lower density, that means my development length needs to be longer. So that works into the equation. Okay. And now on the second term, right? On the second term here, this is the strength related. Fy is the yield strength divided by f square root f prime c is the compressive stress of concrete. And I can add a little bit flavor to this square root here. So square root is something related to the fracture of concrete microstructures. Okay. You can just say it's related to fracture of the concrete. So this terms here is the ratio between the yield strength of the bar and the concrete compressive stress. So think of it, the higher concrete or the stronger concrete is, the shorter length you need to develop the steel into the yield strength. And of course, the higher yield strength the steel has, it takes a longer development length to build that stress, okay, to build that stress. So that is the second term. So the first term you can think of it as just empirical equation, 3 over 40, that's a fitting coefficient. Lambda is the weight of the concrete. And the second term is a ratio between the strength of steel and the strength of concrete. And the third term here is a complicated term, right? So on the top, psi t is a position related term. Position related term. That means if I have more than 12-inch concrete underneath it, I takes more length to develop, or shorter lengths or longer lengths to develop, right? So you take a look at the psi t here, says if has 12-inch of concrete underneath it is bigger than 1, is 1.3. That means it takes a longer length to develop the stress, okay? Now if psi t, if psi t is below, if there's more than, if it's less than 12-inch of concrete underneath it, then you don't have to worry about it, okay? And again, the reason is because the more concrete under the bar, it has more of aggregate segregation. Again, I want to give a picture of what is aggregate segregation, right? So if you're ever on the side pouring concrete in, right? When they start pouring, you see all these eggs, right? Pouring together with the cement. Cement, I use that, right? Together into the tank, into the formworks, right? So as you have more depths underneath the bar. So let me use a different color for the bars. Okay, so these are the bars that has been tied to the formworks, right? So as the pouring is getting to the end, all these aggregates, okay, all these aggregates will probably going to be accumulated at the bottom here. Okay, and all the cement is probably on the top. And when you have more than 12-inch of a depth of a concrete built up underneath the bars, so your bars are not surrounded by aggregates. Okay, the bars are not surrounded by the aggregates. So when I try to apply tension, which is out in and out the plane direction, stress the bar, the concrete can easily get cracked. The concrete can easily get cracked. Okay, so that's why it takes a longer distance to build up the stress in the bar. All right, so that is the reason for psi t. That is a reason for psi t. Okay, so one more information is about the coating psi e. Okay, so when the rebar is coated by epoxy, that is for the protection for anti-corrosion protection, right? You have a thin layer, right? So looking at the picture here, you just have a very thin layer, usually it's green color, thin layer of plastic, right? Wrapping around the steel bar, wrapping around the steel bar, okay? And when I have a thin layer of plastic wrapping around the steel bar, what happens? What happens is that this thin layer of plastic sheet acting as a lubricant, right? When I try to pull the bar away, it simply will try to slip, right? Will try to slip, right? So this slipping action reduces the adhesion and the friction at the contact. So it takes a longer distance to build it up, to take a longer build distance to build it up. So for you, just need to remember if you have coating on the bar, it's either going to be 1.5 or 1.2, depends on the concrete cover that goes into the psi E. That means it takes longer to develop. And last but not least, psi S, right? Psi S is a bar diameter property, bar diameter property. Okay, why is that? As you think of it, what's truly happens is that if I have a bar, and this is zoomed in portion, okay, I have ribs. Now, although the ribs were built in such a way they're proportional to the diameter of the bars, okay, they're proportional to the diameter of the bars. Okay, the larger is the stress distribution across the bars are non-uniform. Okay, if I draw the stress distribution in the bars, they roughly follow this exponential term. Okay, exponential term. So when I have a bigger bar, it's more non-uniform. Okay, so it takes a little bit longer development length to build it up. Okay, so that's the bar size diameter, sorry, bar size effect, bar size effect. Okay, the most complicated thing in the last, well, in the third term is this confining effect term, CB plus KTR divided by DB. All right, now CB is simple, it's just the concrete cover, right? And KTR is a confinement effect. This is the complicated part, right? So when we show the KTR, there's an equation for it. It's a 40 is a fitting coefficient divided by S is spacing between stirrups, ATR is the cross-section area, and N is the number of bars being developed. There are so many N's in these lectures, in these courses, so make sure you differentiate. This is not a modular ratio. This is a number of bars being developed, okay? I provide a detailed drawing here to show you how to use this equation. Make sure you understand that, okay? Make sure you understand that. And the last term, but not the least, is the dB is the diameter of the bars, diameter of the bars. And end of it, once you compute it, the development length, right? It has to be always bigger and or equal to a foot, a 12-inch. And that's the minimum development length you need. All right. So at the end of this lengthy review, right, we eventually presented a very long equation, to calculate the development length. However, we may not use this very often. Why is that? It's too difficult to use. As you can see, too complicated. I have to judge by the coating, the epoxy, the position of the bar, the bar size, confinement, yada, 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 too much, too much. And for a field engineer, it's too complicated. All right. So ACI says, you know what, folks, we have a simplified version. And what does this simplified version look like? Okay. So this is simplified version look like. So simplified tension, okay, development length. I want you to be careful, okay? This is under tension, okay? This is under tension, all right? So ACI says in table 25.4.2.2, I can simply divide all my scenarios into the following cases, okay? ACI says, look, I can divide my all scenarios of my case into simple cases. First, I put the first category as a spacing, okay? That means concrete space, bar spacing and concrete cover, okay? And then I divide the conditions in two categories. One is that number 6 bars or smaller, number 6 bars or smaller, and the other is number 7 or larger. Smaller bar, bigger bar. Okay, so now with this, I can declare my cases. So I will say case one, my write up is messed up. Okay, case one, okay, is the case that 1.1 actually, first category of case one is that when my clear spacing, okay, is bigger than dB. Okay, so just give you a picture. Clear spacing means the pure space between bars, okay, bigger than dB, or clear cover, okay, clear cover, okay, bigger than dB, okay, and and stirrups ties means I do have stirrups, okay, I do have stirrups, okay. So this is the case 1.1, okay. So ACI said under this scenario, my development length LD equals to a simpler equation that is Fy psi t and psi e. These two coding efficient factor and position factor still there, divided by a 25, lambda still there, square root f prime c multiplied by dB. Okay, it's much cleaner. No more 3 over 40, no more square, sorry, no more psi s bar parameters. It just is clean, right? Clean. And if it's for number 7 or larger, LD equal to a Fy psi t psi e divided by a 20 lambda square root of f prime c and dB. Right? So you notice that for number 7 and larger, this number is smaller. This number is smaller means longer distance. Okay, so this is case 1. Okay, case 1. Now, actually case 1.1. Okay, now also there are case color is messed up. Sorry about that. There's also a case of 1.2. All right, case 1.2. It says clear spacing is greater than or equal to 2 dB, 2 times of the bar diameter, okay? Or clear cover is bigger than 2 dB, okay? More concrete protection. And the ACI says these two cases, right, all falls in case 1, okay? And use the simplified equation for number 6, use this, number 7 or above, use this, and that's it. Much easier to calculate. You don't have to worry about the KTR, the confinement effect, all that. Don't have to worry about it. Okay. And then ACI also says, now if this is case 1, what are the case 2? Case 2 is everything else, right? Everything else, others. For all the other cases, ACI says use LD equal to 3 times Fy, yield strength of the bar, psi t, location or position factor, psi e, coding factor, divided by a 50 lambda square root of f prime c, bracket outside dB. Okay, 3 over 50, a little bit smaller than 25. Okay, and for number 7 bar or bigger, you use 3 Fy psi t, psi e divided by 40. This coefficient still is here. Lambda square root of prime c bracket outside dB. Okay. All right. Okay. So these are the simplified table. Okay. Let me close out the table for you so it looks more legit. Right. Some people say my table is open-ended. It doesn't sound right. So let me close it up for you. Okay, nice looking box, right? So this box, I want you to remember, like you remember the code for your email account, right? Remember it. Okay, so this is the table where we use simplified approaches. And we love simplified approaches because it's just easier. Now, at this time or at this point, you observe this simplified version, so-called simplified version, and compare that to the lengthy long development equation version, right? What is really missing is this confinement term, or CB plus KTR divided by DB term. That is what's missing here, okay? So why this can be omitted? It is because, right? Because, right? In this case here, I forgot to put in here. Let me use a different color, okay? Case one is CB plus KTR divided by DB, and that is greater or equal than 1.5. Okay, means you still need to calculate it, but you don't have to incorporate an equation. Just have to do a check. And here, CB plus KTR divided by DB, that has to be greater than or equal to 1.0. Okay, so that is where the confinement effect plays in this table here, Okay, all right. So at this point, we have arrived at a simplified version to calculate the development length. Okay, so I'm gonna pause here. Any questions so far? Folks, are we okay with this? Any questions on this? All right, okay. So if it's not so many questions, right? Let me just quickly take a look, right? So we have two approaches now, right? This is called the conventional approach, okay? Conventional approach. Okay, some people also like to call it basic approach. Basic approach means universal, means if you forgot everything, right? You lost your code, you lost your computer, right? You use this equation. I doubt you still remember this equation, but you use this equation, right? This is called the basic approach. At the end of the day, if you have your code with you and you're smart, you know, you don't want to do a whole lot of work, you use this. And this is the simplified approach. Simplified approach. All right. Okay. Now, if you are a nerd, just like me, right? You say, you know what? I like to do both. I like to do both, right? I love reinforced concrete so much. I want to do both. So I'll end up with a conservative result from the basic approach. Okay. That means if I calculate using the two approaches, you will find that the development length computed using the simplified approach is always larger or equal to, larger than or equal to basic approach. Okay, so this will be more conservative, and in a sense, in a nutshell, longer. Okay, longer. So you sacrifice, right, your speed for, you sacrifice your length for speed, Okay. All right, that's about as dry as this lecture can get, right? So moving on. Okay, I'm running out of time, so I only spent 10 minutes for the example, and we'll continue example on Monday, but let me just get started, okay? So lecture 23, somehow I couldn't get the name right, so bear with me. Lecture 23, development length continued by example, right? I want to see how this in the practice, okay? See this in the practice, development length, okay? All right, so I want you to use both approaches.
Dr. Wu?
Yeah.
I think your screen is frozen. I can't see anything other than table.
Let me reshare it, okay? Sorry about that. Okay, like I said, my Thursday's internet not so friendly day. Okay, give me 1 second. And Jane said the same thing. Thank you, Jane. Is it better now, Corey and Jane? You guys can see, can you guys see it?
Yeah, that's good.
Okay.
Yep.
Yeah, sorry about that. So like I said, this lecture 23, we're going to walk you through an example of use both, okay, use both conventional or basic, okay, or basic approach and simplified approach, okay, to calculate the development length LD, okay. So how do we calculate it, right? So example looks like this, I have a section that is an old-fashioned rectangular section, old-fashioned rectangular section, and I know the details of the section. Say it has a width of 12 inches, okay, a pretty narrow beam, and a height of 20 inches, okay, 20 inches. And I say, I have bars being developed on top, okay, bars being developed on top. All right, so I have bars here. Let me use blue color. So 1, 2, 3, 3 bars, okay, and let's just say 3 number 8, 3 number 8. All right, and then I also have a stirrups, a hoop going through them, okay, for shear and for confinement, okay. And I will tell you straight up, say, look, I know for a fact that when I pour this concrete, it's upside down pour, and I have more than 12 inch of concrete buried underneath the bars, okay, buried underneath the bars. All right, and let me give you some properties, right? I say, look, the concrete is 4 KSI, curbside concrete, and the strength for bars, yielded strength is 60 KSI, and the psi factor immediately, because I have 12 inch underneath, right? So it's 1.3. Okay, I give you already. All right, and I have stirrups, which is number 4, at a spacing of 8 inch. Okay, stirrups number 4 at the spacing of 8 inch. So number 4 at 8 inch. Okay, all right, and on top of that, I will say that there are 1.5 inch of concrete cover, 1.5 inch of concrete cover. Okay, and that is to the edge of stirrups, to the edge of stirrups. Okay, I was never so peculiar or specific about this concrete cover business because we were not talking about development lens. But for this, we have to be very exact to the edge of stirrups. That means, right? So if I want to zoom in, okay, zoom in. So let me put a drawing here. I say, I want to zoom in this as a magnifying glass. Okay, so this would give me what? This would give me the detail, right? So the detail looks like this. If this is the stirrups, okay, this is the stirrups, and this is the center bar, this is the corner bar, and when I draw this, my corner bar is not drawn right, but that's what it is. And the concrete side is here. When I say 1.5 inch, that means this is 1.5 inch. Stirrups is what? Number 4. Number 4 is what? 0.5 inch. And bars number 8. So to the center of bars here, this one is half dB, so 0.5 inch again. Okay, so if I want to say the concrete cover from the edge concrete to the center of bar, I have 1.5 plus pi plus 0.5. So that's like what, 2.5 inches. All right, but anyway, this is the zoom in. Okay, this is zoom in, and we need it. We need it. Okay, which I will show later. All right, so now take a look, right? I want you to calculate the development length for this, right? And we say we want to use 2 approaches. We want to use 2 approaches. So what are the 2 approaches? Conventional approach and the simplified approach. So let's go with conventional approach first, right? I'm such a classic guy, so I want to use conventional approach, right? So switch color here. Let me use black sort of. Okay, so a conventional approach. Right? I love long equations. I just want to evaluate and take a look at it, right? So the equation is LD equal to, if you remember, which I doubt you do, but remember now, 3 over 40 lambda multiplied by Fy square root of F prime C and multiplied by psi T, psi E, psi S divided by a confining factor CB plus KTR divided by a dB. Okay, and the whole thing bracket multiply a diameter of the bar dB. And don't forget, this whole thing has to be bigger than or equal to 12 inch. Bigger than or equal to 12 inch. Okay, so all this has to also satisfy the criteria that CB plus KTR divided by dB. That is the confining factor has to be smaller than 2.5. cannot exceed that, and KTR equal to equation of 40 divided by S multiplied ATR, transverse reinforcement area multiplied N. And you notice that to differentiate, I use a capital, use a small n, but you can use the capital N as before, is the number of bar being developed. Okay, I will label here to be developed. Why is that? Because I got confused by it once. I don't want you to get confused. Okay. All right. So this is it, right? I'm going to use this equation. So take a look at the coefficient first, right? Take a look at the coefficient first. So psi t, we know is 1.3 since more than 12 inch of concrete underneath it. Okay, under. Okay, under what? Under the bar, right? And then psi e, you know, I say it's 1.0 because it's uncoated. We'll call it bare bar, right? Bare bar, uncoated bars. Okay, and then psi s, which is a bar size coefficient, say is 1.0. Why is that? Because it's a number 7 bar, sorry, or bigger, right? Or larger. What we have is number 8. Okay, what we have is number 8. So we're okay. All right. So now these are the coefficient, right? Not too bad. Now I'm looking at this factor here, confining. So I start looking at CB, concrete cover. Remember what is CB? CB is minimum of C1, C2, so on and so forth. But in my eyes, right, I want to do drawings. I'm going to visualize the guy. So everything's graphic. I want to see it. So essentially, this is my bars, the corner, right? In this case, my section looks upside down. So that is my corner, right? So I have CX, which is from edge of the concrete to the center of bars, CX, and the CY edge to the center, okay? And I need to know the minimum of CX, CY, okay? Or what? Or bars, between bars, clear spacing between them, right? Clear spacing between them. So if this is CC, so I need to know if CC divided by 2, so avoid any confusion. This is CC, then I need to know CC divided by 2 is also in this here, okay? So let's take a look. What is CX, CY? Which one is minimum? On the side, right? Take a look. I have a 3 bars, right? 3 bars, okay? And this is 12 inches, which is quite long. So I'm pretty sure that this edge is big. So I don't have to worry about it. It is CY, I have to worry about it. Now, what is CY? If you forget, right? Go all the way back to the zoom in picture when I said we need it. Remember, we need it. It is because CY here equal to 1.5 plus 0.5 plus 0.5, and that is 2.5. 2.5, isn't it? 2.5. So CY, okay, CY equal to a 2.5 inch. All right. What is CC? What is clear cover? Right? What is clear cover? So I don't know what is clear cover, right? So CC divided by 2, I don't know. So how to find this? We need to take a look at the bar details. And I promise you it will be 2 more minutes, okay? Bear with me for 2 more minutes. So CC is the bar detail, right? So we need to take a look at the section again. So this is the section, right? Upside down, right? Bars on the top. And I have 1 bar, 1 bar, 1 bar. Okay, now the whole thing is 12 inches. Whole thing is 12 inches. And when say the concrete, right? The concrete cover is at a distance between the edge of the concrete to the stirrups. So let me just draw the stirrups up. Okay, draw the stirrups up. And don't forget the stirrups also has a side. All right, so this has a distance of 1.5 inch. Okay, now I'm going to assume the corner bar sits right here at the edge of the stirrups, which is not true, but this gave me that, right? Let me make that assumption. Okay, so I assume this is about ½ inch of stirrups. Ease my computation, and the center of the bar to the edge of the bar is another 0.5 inches. Another 0.5 inches. Okay, now if I do this, right? If I do this, I can say this. Now the clear spacing between them, the bars C2, is equal to 12 inch, which is B, the whole width of it, minus 1.5 inch multiplied by 2. Why multiply by 2? I have a 1.5 here. I also have a 1.5 here. Okay, so multiply 2 minus 0.5 inch multiply by 2. Again, multiply by 2 because I have a stirrups here, stirrups here, I have stirrups here, right? And minus 0.5 inch multiplied by 4. Oh crap, what are these for, right? So I have a half bar, half dB here. I have another half dB here. I have a half dB here, half dB here, half dB here. So I have to exclude them out, right? So that's why half dB multiplied by 4. And then that total thing divided by how many spacing I have? Number 1, number 2, 2 spacings, right? So that is my clear spacing between bars is about 3 inches. Now be careful. See, I was very careful. I said it is about 3 inches. It is about 3 inches. Why is that? Because I neglected, and I won't admit, I neglected the gap. If you remember, right? Oh, if you remember, we talked about this in the bar detail section, right? I neglect the gap between the stirrups, if you remember, and the bar. There's a small gap here, neglected. You say why? Because I want to be a bigger C2. I want to have a bigger C2. Okay. All right. So it is okay to neglect here. Okay. Neglect here. All right. Okay. Anyway, so that is a concrete clear spacing. So C2 is 3 inches. So C2 divided by C2 divided by 2 here is 1.5 inch. 0.5 inch. All right. Now I want to find the minimum of CY 2.5, CC divided 2, 1.5. Which one is minimum? So naturally, right? Naturally, CB equal to minimum of 2.5, 1.5, and 1.5 wins. Okay, this is our folk. This is our folk. We select 1.5. All right. Okay, so with CB selected, I can compute my CB multiplied by KTR divided by DB. And we need to evaluate KTR using the transverse reinforcement, which we will talk about it on Monday. Okay, which we'll talk about on Monday. All right. Okay, I think this is a good point to stop. I'm going to stop here. If you have any questions, stay behind and we can talk about them. All right. Or else I'll see you on Monday. All right. And on Monday, we'll go through this example and we'll talk about the lab or the design part. Okay. Thank you very much.